Okay, so in this video, we're going to be talking a little bit about functions versus relations. Now, functions and relations can be represented in a whole bunch of different ways, and this is not in any way exhaustive. You will sometimes see these bubble diagrams where you will have the starting or the input value represented with a list of values. And then there will be arrows pointing to a second bubble with a second set of list of values. These values do not have to be numbers all the time. These like concepts of functions and relations exist regardless of whether we're talking about numbers, even in mathematics. We often use numbers because they have, you know, properties that are useful to us for doing our analysis. But again, we're in no way confined to numbers. We can also list our functions in terms of just a list of points. So pairs of coordinates. You could also plot these points, for instance, to get a graph of these points. So for instance, this list of points could be represented graphically with a graph like this. And again, I'll shrink it so we can see the whole thing. And this is just, again, a plot of the points that are in our list. So these are equivalent representations. We can also represent things in a table. Again, in a table, we're assuming that the pairs are going together, although you can basically treat this like a bubble diagram, as we saw above, where you actually indicate arrows that connect things. But typically, when things are in a table, you assume that the pairs are like the coordinate points, that Betty goes with Tom and Pam goes with Toby and so forth, so that the lines are actually representing who goes with what. And then finally, we can also represent our functions or our relations with equations. In a two-dimensional case, like what we're working with in this class, we would typically start out with just two variables, so x and y. You can think of x as the input, y as the output, but the relationship is complicated. In some cases, other cases, you can represent them very straightforwardly with a nice simple equation. If you know what the input is, then there's only one possible value for the output. And we're going to talk about how these two cases differ. But all of these are examples of ways that you can express relations. Now, when it comes to dealing with the difference between functions versus relations, then functions are a subset of relations. And functions are a subset of relations where there is, for every input, there is exactly only one output. It is a relation, but for each input, x, there is only one possible output, y. This is, again, the definition. So we can look at our table here, for instance, and we can see that this does constitute a function. All of our x values in our list of x's are unique. They're not repeated. And each of them is corresponding to one y value. So Betty relates to Tom, Pam relates to Toby, and so forth. There are no duplications. Now, in an equation of this form where you're able to solve for y and not have, you know, weird things like plus and minuses or two y's in the expression or things like that, then you get a function. So particularly here, we have y on one side by itself. And so I can easily see that if I pick a particular value for x, I'm only going to get one outcome when I multiply it by 2 and then add 3. There's no way that I can get two outcomes from that. Now we're going to see, and we can do this graphically, we're going to see that if we actually plot this other relation, that in fact, that's not going to be the case. If we look at our list of points, again, we can either do this graphically or we can do this by looking at the list. For each one of our x values, there is only one y value. So there's only one in my list. in the first coordinate, and it corresponds to a 4 in the second coordinate. So if I know the input is 1, I know the output is 4. If I know the input is 0, I know the output is 3. If I know the input is 4, I know the output is 2. If I know the input is 7, I know the output is 1. That's 7, 4, 0. Those are not repeated anywhere. So each one of the x values is unique, and each one of those is giving me a y value. Now, the fact that the y values are repeated is not a problem for a function, because if I know that I have 1 as an input, I get 4 as an output. And I know if I have 2 as an input, I also get 4 as an output, and that's fine. If I think about this graphically, what that means is I can think of my x coordinates down here on this horizontal axis. And as long as I don't have any points lining up on top of each other with the same x value, then I can think of this as a function. Now, if I look at my bubble diagram, I immediately see that this is not a function because D is pointing at both pink and at, it looks like, tan. So if I want this to be a function, I would have to remove one of these arrows. Now I have a function. So now I have A pointing at one value, B pointing at one value, C pointing at one value, D pointing at one value, E pointing at one value, and F pointing at a single value. Again, the fact that the y values are repeated is not a problem. I can't have x values repeated. So this would be a function, but the original example where D is pointing at 2 values is not a function. It's just a relation, but it's not a function. Now, we mentioned with the list of points that I can, if I'm thinking about this graphically, then I can look for any x value and I can see if there's 2 points that are associated with that same x value on the graph. I can actually do the same thing for equations. So for instance, in this equation, x squared plus xy plus y squared equals 12, I might want to wonder, well, is it possible to solve this for y so that it is a function and not a relation? And I can do this by graphing without having to actually do the algebra. I can look for that telltale signature of functions, whether or not there's, for each x value, there's only one y value. And if I plot this graph, and again, let's shrink this so that we can actually see the whole thing. This graph produces this function, this equation produces this graph. And you can see this is basically an ellipse that's sort of tilted on its side. And what we have here is if you pick any x value that passes through the graph, except for the one way at the far right and the other one way at the far left. Nonetheless, if you pick a value anywhere in between, then there's a point here that has the same x coordinate as a point here, but they have 2 different y coordinates. So this is not a function. This is still a relation. Everything is a relation that relates 2 variables, but it is not a function. And so what we have is called the vertical line test. The vertical line test says that if the graph of a function touches a vertical line in 2 places, it's not a function. If the graph of a relation touches a vertical line in 2 places, it's not a function. Whereas if you were to plot our line y equals 2x plus 3, then that is just a line on the diagonal, and the vertical line will only cross in one spot. So there's a couple of different approaches that we can take in order to determining whether or not we have a function. Again, in the table case or in sort of the bubble case, or even in the case of the list, the thing that would give us away that we're not a function is if we were to list the x values twice, or in this case, have arrows leaving the same x value more than once. Now, there is one other concept that's associated with functions, and that is whether or not the function is one-to-one. Now, this is something that will come up a bit later when we start talking about inverses. But the general idea of a one-to-one function is that each input maps to only one output, and each output comes from only one input. So there is as we say, a one-to-one relationship. One input, one output. There is a unique combination of inputs and outputs. Now, obviously, if it's not a function, then that doesn't satisfy that. But for these other ones, the one-to-one relationship requires that each output also be unique. Now, if we go back and we look at some of our examples, even if I make this, take this one away, make it a function, this is not a one-to-one function because red is used twice. If I look at my list of points here, I'm looking for repeated y values in the one-to-one case. So here I have two repeated y values, 4 and 4, and those are the same y. Again, y is my vertical axis. And if I draw a horizontal line through this graph, there is at least one place where there are two outputs that are the same, two y values that are the same on my graph. That's not one-to-one. It is still a function, but it's not a one-to-one function. In my table example, my x and y values are never repeated. Every x value has a unique y value. So this would be a one-to-one function. Again, my ellipse here, this is not a function, and it's certainly not one-to-one. Again, for any y value that goes through the graph, most of them are going to touch in two different places. So there's two ways that I can get any output value. Now, for the straight line, I could actually do a little bit of algebra on this and show that if I solve for x, I will get a unique output based on my y input. So for this one, if I start with y equals 2x plus 3, then I can move the 3 over and then divide by 2. And again, in this kind of a relationship, what this is telling me is that if I pick any y value as my output, and then I subtract 3 from it and I divide by 2, there's no way to duplicate that. There's no way to sort of multiply the number of inputs that I would get that correspond to that. There's only one output that is possible. Pick an input, multiply by 2, add 3. It's not duplicating. And so I'm getting one output. Same thing, if I start with the output, I can back out to get whatever that unique input was. That's the classic telltale sign of a one-to-one function in equation form. So I can solve for x, I can solve for y, and I don't have to worry about any pluses and minuses or weird piecewise gyrations. It's just straightforward algebra. Now, the one-to-one functions have a test similar to the vertical line test, but it's the horizontal line test. And it basically says if the graph of a function, because we're starting with the assumption that it's already a function, touches or in fact, any horizontal line in two places, it's not one-to-one. Now, early on in algebra, we're mostly concerned about whether or not our equations or relations are functions, but the property of one-to-oneness is going to come up again later on when we start talking about inverses, which will be a very important concept as we build our function repertoire.